Synthetic division can seem mysterious, but it's really nothing more than a shortcut developed from observing patterns. Here we're going to look at how to derive it. I'm assuming you're completely familiar with synthetic division already, and so I won't be teaching it here. There are tons of videos on that if you feel the need to review. They're all over the internet. So here what we're going to do is go completely symbolic with variable coefficients and then look at the resulting patterns. So I would, of course, do this divided by this, the two first terms. That would give me ax squared. I don't necessarily write stuff in a particular place up here. Down here you have to do columns and stuff, but not really on top. Okay, well now we would do this times all of this. So that's going to give us ax cubed positive a and x squared. And then of course we do our subtraction. So this is the way I do it. I like to put parentheses around the whole thing and just a single minus in front. This of course all goes away, which is the whole point. And now we have to combine these and take into account this. And so if I have this many x squareds minus this many x squareds, well then I'm going to have this many x squareds. And then of course we continue the subtraction by bringing this down. It's just minus nothing. Okay, so that was one iteration. This is a degree 2 and a degree 1, so we can do it again. So if I do the two first terms, this term divided by this term, I should say, then we're just going to have b minus a m x. Now we do all this times all this, put it down here and subtract. Okay, so this came from this times this, so that m just has to distribute to each of the two terms there. Now we subtract again. Use a square parentheses so it's easier for the eye to follow because I have parentheses inside of parentheses here. This of course all goes away, and here we get, so I have this many x's and this many x's, and we have this subtraction. So if I have this many of them, and then remember, subtraction just flips the signs of all terms. So we're going to have minus b m positive a m squared, and that's how many x's we have. Okay, well now I have a degree 1 and a degree 1. Remember, the denominator, sorry, not the denominator, the remainder has to be a degree less than this thing. So so we can go one more time. So if I do this term divided by this term, it's going to simply give me c minus b m plus a m squared. I'm using parentheses to group things, so it's easy to keep track of everything. You'll see more what I'm going to do in a minute. We do the multiplication, and we get we get this. We do our subtraction. This all goes away. And now this is just a constant minus a constant. So it's just going to be D. And then remember, this is going to flip all of these terms. So we're going to have negative CM positive BM squared minus AM cubed. Okay, now this is a degree less than this, so we're done. This is our remainder. Okay, well, so to derive the shortcut, really the thinking is something like this. Okay, we really just want to look at the coefficients. That's all that we're really trying to figure out with synthetic division. We don't need to keep writing all the x's over and over. If we just have the coefficients and the remainder, well, then all we have to do is put the x's in and we're done. So let's think about this a minute. So does it make sense that instead of writing all of this stuff here, if you were given a division problem and all you, well, let me say that differently. If you just take the four coefficients here, or however many there are, I just happen to have four here, and this number, does it make sense that just with these alone and using these patterns, you could find the coefficients of the solution of any polynomial division, assuming this is 1, of course. We'll talk about that later. It's more complicated if that's something other than a 1. That's really all synthetic division is it's just taking these things here and looking at these patterns and quickly figuring them out without going through all this stuff. And so technically, if you memorized these or you had them written down, well, then you wouldn't have to do all of this stuff here. You could just simply follow the patterns with these numbers and have the coefficients, and then you put the x's back in. Well, that's not very practical. So what we're going to do is take it a step further and see if there's a way that we can make these patterns happen without having to memorize them or have them written down. So what I'm going to do, so pretend you're the first person thinking this out, which actually that was Paolo Ruffini, an Italian mathematician in the early 1800s. He's the one that came up with this. But I kind of want you to think about the fact that you could probably have done this too if you really set your mind to it, because it's just about paying attention to patterns and creating some steps that you're going to do the same thing over and over. And so how could we figure out some kind of maybe an algorithm where we can make all of these patterns happen automatically without having to memorize? So let's say we're experimenting and we take the coefficients and we write them in a line here, and then we know we need this number. We're not using the x's, of course. That's part of the whole point, is making this quicker, because we don't need to keep writing the x's over and over. And is there a way we could maybe make these four things happen down here just by following a certain number of steps? For one thing, it kind of makes sense. There must be a set of steps that would work to do this, because this whole thing was pattern based. We just kept doing the same thing over and over. So how could we get this? And that's where we could see, well, hey, it's right there. So we can just bring that straight down and that one's done. Okay. Well, now I want to get this one, is there something we could do to make, and I'm going to write it here first because that's the goal. So if we were thinking this out, we could think, well, how would I make this happen with this, this, and this? Okay, well, you might mess around a little bit and then finally realize, okay, well, it would be really convenient to put a negative on this, whatever the opposite sign is of this, because if I do this times this, that would give me negative AM. And then I just combine these and boom, there it is. And so we figured out a little pattern that we could do to make this happen. And now it kind of a good guess is if we do that again, the same exact thing, well, we would kind of expect that what we get here to be the same thing as this, because this whole thing is just so pattern based. So let's try it. So let's do this times this and put it here. So that would be negative BM positive AM squared. And now let's just combine these. So we would have the positive C, the negative BM, and the positive AM squared. And sure enough, that's what happens. So we have worked out a pattern that will make all four of these, or however many there are, happen just using these and using our little algorithm system here. And so that last one, I'll just do it quick because the same thing's going to happen. So if I just do this times this and put it here, and we combine, and we get exactly this. And then I'm sure you already know the way we would put the x's back in is we would think, okay, I did a degree 3 divided by a degree 1. So this would have to start out as a degree 2. And this of course would just be a number. And then there'd be a plus in here and all of this. And then all of this, since it is a remainder, it would go over the divisor. So I'm assuming you already know all of that. Okay, so that's really all synthetic division is it's just a matter of thinking out what patterns happen and then finding a convenient way to do those patterns without having to have stuff written down or memorized. One last thing that I'll close with. So you've probably been told not to use synthetic division if the leading coefficient of the divisor is something other than 1. Here, this would be a leading coefficient of 1. But if it's 2 or something else, something other than 1, then you're not supposed to do it. Why is that? Well, there is a way to do synthetic division. If that's the case, if you had like a 3 on here or something, there is a way to do it, but it involves extra steps that make it so much work, it doesn't really save time, so it's not practical as a shortcut. So unfortunately, that just means that this method is really, synthetic division is really only practical if the leading coefficient is 1.